Dear students, welcome back. So we are going to continue with the optical fiber, and in this class I am going to take attenuation and fiber loss. So let us see in detail. Now let us see what is the attenuation. An optical signal propagating through the fiber will get progressively attenuated. It does mean attenuated does mean its intensity is going to decrease. So it is getting attenuated does mean its intensity is gradually decreasing. So let us suppose here we have taken an optical fiber. This is the optical fiber that we have taken, and through this optical fiber we have launched any signal through this, like let us suppose we are launching. So this is called your input signal. So Pi, I am representing this. And here we have got the output signal. So here we have the output signal, and this output signal I'm calling as PO. So what we find, if it is going to pass through a length L, let us suppose it is going to pass to a length L from here to here, then what we find that at the end its intensity is decreasing, as you can find out from this diagram, and that is called attenuation. This is what I have tried to show you from these two birds. As you can see, this bird is containing with all the colors, right? But as it's a progressing, that is, let us suppose it is going from one place to other place. In the sunlight, there is a rain, there is a lot of heat, and all those things are there. That is, there are many external factors, as well as let us suppose bird is getting older as well with the time. Then what is happening, its color is slightly getting faded. So now here you can see it's your something in the green, it has become now black. So what is happening, its color is changing, and that is called attenuation. So if there is going to be change in the intensity, that will call attenuation. So this attenuation, what will the value of the attenuation if it is going to travel for a particular distance L, right? And that has been mathematically calculated, and that is given by alpha is equal to 10 upon L log Pi upon PO, or Pin does be input and PO is output. So this alpha is called your attenuation coefficient. So this is how following this equation the intensity is going to be attenuated, right? So I think you must have understood this. Now let us suppose we are saying P input is equal to P output. That is, whatever we have launched, the same signal is going to come out. Then what we say, the value of the alpha will be 0, and that will be the most ideal case. But in reality, this does not happen. Even the most ideal optical fiber will have the loss, and that loss is minimal at the level of 3 decibel per kilometer. That is your minimal loss through your optical fiber. We have a different range of the fiber depending upon the types of the fiber, whether say single mode optical fiber or say multi-mode optical fiber. Depending upon the type of the optical fiber, we have a different type of the losses. All right. Now in the next slide, we are going to see what are the reasons of the attenuation. So naturally, what can be the reason? Now it is going to pass through the optical fiber. So optical fiber is a pathway through which it is going to pass. So naturally, that pathway also may have the different properties, right? As you say, if you are passing on the road or you are traveling on a road, so your speed is going to depend on the many factors. Your road should be very good, your car should be very nice, the road should be wide, right? There should be less number of the traffic and all those things. So depending upon that, you will have the speed, and in that way, if you are going to maintain a very good speed, then in a very small duration of the time, you can reach from one point to another point. So let us suppose now let us see what are those factors within the optical fiber or outside the optical fiber which is going to affect the intensity of the signal which is passing through that, and that is going to be called as attenuation, and those factors will be called as fiber loss. Now here let us suppose here I am firstly trying to show you with this diagram. In this diagram I have plotted the loss per decibel per kilometer. So as you can see here, this loss is increasing, so it is in increasing order, and here I have taken the wavelength. Here I have taken the wavelength, and wavelength is also in increasing order. So here we have got the minimal wavelength. If we have got the minimum wavelength, it does mean we have got the maximum frequency. So here what we can see here as the minimum wavelength, then here what we are getting, the loss is maximum. As the wavelength is increasing, as you can see, as the wavelength is increasing, loss is decreasing. So what we can say, the light is a carrier. So what type of the wave we are going to use to take out the signals? So what is the wavelength of the light that we have chosen? So naturally your loss will also be dependent upon that. Now we see here I have also taken other factors, like here we are saying, here I have written here OH absorption peak. What it does mean, OH absorption peak? Now optical fiber is going to receive certain moisture in the path, because it is passing through the optical fiber, and it may be under the ground or wherever it is, it may receive certain hydroxide, and because of that hydroxide which is getting embedded in that, at one particular wavelength, you see you are getting certainly a peak over here. So at different wavelength, now you can observe the peaks, and this is because of the certain external impurity that has got embedded in this, right? Similarly over here you can see here I have tried to show you what is happening if the infrared rays we are going to use. So if the infrared we are going to use, that is the carrier of the light is the infrared, then again here you see at one particular wavelength you have got the sudden increase, right? So there are different regions, right, due to which we can have the loss, and therefore this is where I wanted to show you first that what can be the regions, and all these have been systematically studied, and a few of them according to your syllabus we are going to study. Now first is material or impurity loss, second is called the Rayleigh scattering loss, the third is called the absorption loss, fourth is called the bending loss, fifth is called the radiation or radiation induced losses, and finally modal dispersion or intermodal dispersion. So these are the different type of the losses which we'll have through the optical fiber. It does not mean we have only these 5 types. We have more, but these are the important regions for the losses, and this is the primary levels. So therefore we have taken all these things. So now let us study one by one. So first is your material or impurity loss, right? So let us see what is this material loss. Now we have already seen that in case of the optical fiber, we have the core and cladding, and through the core the light is being launched. So light will be passing from one end to another end, right? But we don't have this pure silica in the core. What we are going to do, because of different regions, because of the giving the strength to the core, we are going to dope the different materials with the silica. And for example, we can dope with the GeO2 germanium oxide, phosphorus pentoxide, barium oxide. All those impurity is being added in the silica to provide the stability in the core. But then if you have added this, then there is the other part of this, that is it is going to affect your communication. So how it is going to affect? B2O3 produces a strong absorption peak at 3.2 micrometer. So as I had shown you there in the previous slide, the graph, right, with the increasing value of the wavelength. So what we are finding at 3.2 micrometer, B2O3 is going to give you the highest peak, and similarly P2O5 produces that peak at the 3.8 micrometer. So what you are getting, if you are going to use 3.2 micrometer and 3.8 micrometer, then what will happen? Your absorption is going to increase, right? And the absorption is going to increase, so of course the loss is going to increase. So this is why boron and phosphorus based dopant are not used in the low loss single mode fiber. So if any fiber that we require to manufacture, right, where we require the loss to be minimal, then we are not using this boron based or the phosphorus based dopant. Now you can ask me, why to dope at all? If you are not going to dope in any of these substrates or any of these materials, you will have the highly unstable core, and it may break. So there are different regions because of which we are doping these materials. All right, let's see further. The introduction of P2O5. Now if you are going to introduce the P2O5, then what is happening? Serves a channel for the gradual build of hydroxide OH minus ions over the long time, which increases the loss. Now what is happening? The OH, that is, it is going to hydroxide ion is going to be embedded in your core, and that hydroxide ion, as I had shown you in the previous slide, is going to increase your loss, and that will be the OH minus is going to be more in the content if you are going to use P2O5. Right, now let us see the next type, and this is your Rayleigh scattering. So the curve that I had shown you here, according to your wavelength. So what you said, that the intensity, that is absorption, is varying like this. This is your maximum value, and this is your minimum value. This is your minimum wavelength, and this is your maximum wavelength. So it depends upon the wavelength. This is your wavelength, and this is your absorption in decibel per kilometer. Decibel dB per kilometer, right? So what we find, it is inversely proportional to fourth power of your wavelength. Absorption is inversely proportional to the fourth power of the wavelength. So what is this? The glass, now why it is occurring this? Why we are getting this type of this scattering, right? So within the silica, let us suppose here we have taken the core. So what we say, the core has, let us suppose, pure silica, but pure silica is not possible, right? Or the silica also sometimes get damaged, right? So then what we are going to get? We are going to get the inhomogeneous medium within this fiber, right? Let us suppose even we don't have the doping, right? But because of the temperature difference, or there may be different regions, because of this, homogeneity of this core is not going to be maintained. And if the homogeneity of this is not going to be maintained, then we will have this scattering. And this scattering was calculated by Rayleigh, and this is called your Rayleigh scattering. So the loss due to the Rayleigh scattering effect varies inversely with the fourth power of the wavelength, and it is given by this formula. So ARS is equal to 359.095 upon lambda to power 4 mu square. Mu is your refractive index of the core, minus 1 into KT and TF, where this symbol have all the usual meaning, which I have already written there, right? So this is why this type of the loss is occurring. It is because of mainly inhomogeneous composition of the medium, right? It is because of inhomogeneous composition of the medium we are getting the Rayleigh scattering. Let us see next. Now here we have got the absorption loss. Now what do you mean by the absorption loss? Now even the purest of the pure material, whether it may be the silica or it may be any materials, if the light is going to pass, because of the nature of that material, some part of the light is going to be absorbed. So any material, through any material, if the light is going to pass, some part of the light is getting absorbed, and that is called your absorption loss. So if it is going to be absorbed purely by the glass of which the core is made, that will be called the intrinsic loss. But if there are other impurity in that, right, in the glass, then we may have the other regions also. So what can be the other regions? Here we have the ion resonance absorption, ultraviolet absorption, and infrared absorption that I have already shown you, right? So because of the change of the property, or because of the some doping that we are going to put there, we can have the ultraviolet absorption and infrared absorption, and we can have the ion resonance absorption. This we can understand very easily. Let us see this. What we can say, in pure fused silica, right? If you have taken the fused silica, the valence electron can be ionized into the conduction electron by light. Now what is passing through that? We are taking the light, and if the energy of the light is nearly 9 electron volt, then your valence electron will be converted into the conduction electron. So valence electron of your silica is going to be converted into your conduction electron, and moment this type of the thing is happening, then UV absorption will start taking place, right? So here it is not because of any doping, it's a pure silica. But here what has happened, the electrons, because of the effect on the electrons, the valence electron is getting converted into the conduction electron at 9 electron volt of the energy, and because of that this is taking place, and therefore it will be called as because of the ultraviolet absorption. And of course then this will call extrinsic, because this extrinsic region, it is not purely because of the property of your silica, it is because of the external factor. So this will call the within the absorption, it will call as extrinsic absorption, right? Okay, let's see further. Impurity are major source of the losses in the fibers. Now we have the impurity, so hydroxyl radicals OH minus, and the transition metals such as the copper, nickel, chromium and cadmium, manganese, right, have the electronic absorption in the near visible part of the spectrum. Now you see in the here visible part is getting affected. Here ultraviolet part was getting affected because of the higher energy, and here what is happening, if we have the impurity like your copper, nickel, chromium and manganese, then because of the electronic absorption in the near visual part, your absorption is going to increase, and of course we'll have the heavy loss, right? So these are the reason due to the absorption loss. Let us see the next one. Now here we have got the bending loss. Now let us suppose here we have taken an optical fiber, see the diagram here over here. Now while we are going to lay down the optical fiber, at some point of the time we may have to bend it. So what we have done here the optical fiber is being bended while we are laying down the optical fiber. Now we know this work on the principle of the total internal reflection. So naturally at no point within the fiber there should be change in the critical angle. So now here you see theta, here this is your critical angle. So here also we have critical angle, and therefore you are getting the total internal reflection, right? Here also by the total internal reflection it is coming, but now here we have bended. So what we have done here, I have drawn a tangent on this, and on the tangent I have dropped the normal, and then what I am finding, this theta is going to change. Now it will not come at the critical angle, it will come at the less than the critical angle. Moment it is coming at the less than critical angle, then from here the light will escape, it will not come back here. So some part of the light has got escaped, some part of the light has got totally internally reflected. Again here also naturally it will not be coming at the at your critical angle, and again because of that again you will have the loss over here. So at many point in the within the fiber it will not be able to maintain the critical angle, and if it is not going to maintain the critical angle, some part of the light will escape from the fiber, and naturally if the light itself has got escaped from the fiber, which is carrier of your signal, so the signal gets weakened and you have the loss. This is called the bending loss. See another one. Now this was the purely external factor, but now here you see, if we are not bending anything, but because of the heat there may be little structural change in the fiber within this. Now here you see this is called your microscopic effect. So within this bit of the change in the structure is we are getting. So moment we are getting change in the structure, now it does not remain the straight line, right? So if it does not remain the straight line, so the light here may not follow strictly your critical angle, and then it may not have the total internal reflection. So after coming here it may not get reflected back, and it will be coming out of the fiber, and therefore again you will have the loss, right? So what we can say, this is your macroscopic because this is a large band, and this is your microscopic because this is a small band, and because of this the signal is losing, that is signal is coming out of the optical fiber. So this is what we have written over here. Whenever a fiber deviate from the straight line path, the radiation loss occurs, right? These losses are permanent for the improperly installed single mode optical cables. All right. Micro bending and macro bending are the two types of the bending loss. These losses are caused by the deformation of the fiber structure. So you must have understood this. Let's go to the, now this is called your radiation induced loss. All right, let us see. Now while we are laying down the optical fiber, I was discussing in the previous class also, sometime you are going to lay down through the oceans, sometime you are going to lay down near the railway track, or sometime you are going to lay down at a height, right, or the at the peak of the mountain, right. So the fiber is getting penetrated continuously by the neutrons, gamma ray, x-ray, right, and because of that then we will have the molecular structure of the fiber may get altered. So what we are saying, the molecular structure of the fiber, that is of the glass, get the structure and the fiber becomes darkens, right. And moment this fiber becomes darkens, then it is going to introduce one other type of the loss, and that will call your radiation loss. All right, now this is your signal dispersion or modal dispersion, or we can say intermodal dispersions. Now what is the modal dispersions? We had discussed in the previous class also. Dispersion is the phenomenon in which the phase velocity of a wave depends on its frequency. That is, phase velocity and the frequency is not going to match, right? Then we'll have the dispersion. The media having such property are termed as the dispersive media. So if this is not going to maintain, that is the phase velocity is not going to be maintained with the frequency, then that media in which the light is going to pass will be called as dispersive media. And this is what happens in case of multimode optical fiber. Now in case of the multimode optical fiber, what is happening? Let us try to understand this. Now here I have defined the dispersion. Dispersion is defined as the signal broadening or spreading while propagate inside the fiber. So what is happening? Let us suppose here you have taken the fiber. So as it is passing, slowly the signal is getting broadened like this. This is how you can say slowly the signal is getting broadened like this, right? Because of this, what is happening? Because of this, what is happening? Information which is to be transmitted through the fiber is first coded in form of the light pulse, and then the light pulses are fed onto the fiber. That we understand that any signal which is to be transmitted through the optical fiber is firstly to be converted into the electrical signal, and that electrical signal is put on your light wave, and that is going to be carried forward. All right, but then because of that, what is happening? A light pulse sent to the optical fiber broadens in time as it passes through the fiber. So as I had explained you over there, as the light is going to pass, it is going to broaden, and this phenomenon of the broadening or spreading of the pulse is known as the pulse dispersion. So because of this, what is happening? The one signal, let us suppose the two signals are passing. So the two signals will be coming out at the different time, and moment the two signals are coming at the different time, if they are not coming together at the same time, right, then that will give you the dispersions. So naturally that is only possible in case of the multimode, where more than one number of the signal has been launched. If you have only one signal, then there is no case of the time lag between the two waves, right? So this signal dispersion or modal dispersion or intermodal dispersion is only possible in the multimode fibers. And this finishes my this class, and in the next class we'll be taking the point to point communication through the block diagram. Thank you very much, and that will be the end of the optical fiber module 3. Thank you very much again.